In this next set of lectures, we're going to talk about prime numbers. Now, unlike previous sections, the definition you're probably familiar with for prime numbers is going to work just fine. We aren't going to need to come up with something more precise or technical. Now, our goal here is going to be to get to a proof of what's called the Fundamental Theorem of Arithmetic, which says that the prime factorization of an integer is unique. Now, again, this may seem like something that's pretty abstract, but as you'll see, it does have relevance both to number theory and to fields like cryptography that use number theory. So this is our definition of prime numbers, and again, this is hopefully familiar to you, right? An integer greater than 1 is called prime if and only if its only possible divisors are, only positive divisors are 1 and p. Right? The only numbers that divide it are 1 and itself. All right, so what do we know about prime numbers? Well, we're going to start with a really very elegant theorem that also has a really elegant little proof. And one thing I particularly like about it in the context of this class is that it's going to give us an opportunity to see a new method for proving things. So all the proofs we've done so far have really been based on combinations of two things. They've been based on a combination of the argument for the rule of inference called modus ponens. That one is P implies Q and P, therefore Q. Right, so if we know this conditional statement is true, and we know that the premise is true, and we've also used variations on universal modus ponens and universal and kind of its cousin, universal instantiation. Remember, that one is P of X implies Q of X, P of A, therefore Q of A, for some specific A in the domain. All right, and those are great. Those are the things that we use to do what are called direct proofs. Most of the proofs that you're going to see throughout this class are written using these two rules. There are others, and the one we're going to use to do this proof is what's called the law of contradiction. You downloaded the rules of inference sheet from the website. This one is on there, right? The law of contradiction. Again, it's based on that idea that a true statement cannot lead to a false conclusion. All right, so the law of contradiction says P implies C, therefore not P. Sometimes it's not P implies C, therefore P. They mean the same thing. Okay, so what this is saying is if we make an assumption, right? If we assume P and this assumption somehow leads us to a contradiction, leads us to an invalid conclusion, then P must in fact be false, right? The opposite of P must be true. Okay, let's see how we can use this, right? I think it's clearer if we actually start getting into the proof. So, clear this up here. What I want to show is that there are infinitely many primes, right? That's our theorem. So to do that by contradiction, here's how proof by contradiction always starts. Assume the opposite of what you're trying to show. I'm trying to show that there are infinitely many primes. I'm going to assume the opposite of that. Assume there are finitely many primes. I'm going to show that this assumption leads me to a contradiction. It leads me to an invalid conclusion. Right, so how am I going to do that? Well, look, if there are finitely many primes, I can list them, right? Okay, so let's do that. Let's let P be the set of all primes. And there's a finite number of them, so it'll be P1, P2 up through P sub n. Okay? There are no primes that are not on that list. Okay, I'm gonna build a new number now. Right? I'm gonna build a new number. I'm gonna make Q equal the product of all of these prime numbers. Right? Plus 1. Add 1 to it. Okay, first thing I want to be clear about is Q is not a prime number. I know it's not. Q is bigger than every number on this list. This is bigger than every number on that list. It is not on that list. Okay, so Q is not prime. Remember, the word for not prime is composite. So Q is composite. What does it mean for Q to be composite? Well, that means that there is a prime number that divides Q. Okay. So let's let that number be P sub I. Okay, so let P sub I be a prime number that divides Q. Okay. This is going to be a problem. Right, because let's try doing this, right? Let's take Q and divide it by P sub I and see what we get. Right, well, this is equal to that first part, the product of all those P's divided by P sub I plus 1 divided by P sub I. And you see how I'm in trouble? Right, P sub I does go into this first part. Right, P sub I is on that list somewhere. We can cancel it out from the top and the bottom, and we're left with an integer. The way we would write this, it's a little bit awkward, but the way we would write this is P1 times P2 times out to P I minus 1. Then we're going to skip I, right, because I got canceled. So the next number will be P I plus 1 times out to P sub n. And unfortunately, I ran out of room, but still plus 1 over P sub I. Okay, if P sub I divides Q, then this thing has to be an integer, and it's not, because P sub I does not divide 1. The only number that divides 1 is 1 itself. And you remember our definition, 1 is not a prime number. So P sub I is not equal to 1, therefore P sub I does not divide 1, which means P sub I does not divide Q. Okay, notice I'm kind of working my way backwards with my chain of reasoning here. If P sub I does not divide Q, then there is no prime number that divides Q. Well, if there's no prime number that divides Q, then Q must be prime, but it's not. It can't be. Q is not on this list. And there's my contradiction, right? If there are finitely many primes, then there must exist a number that is both composite and prime, but there isn't. There is no such number, right? There is my contradiction. How do we resolve this contradiction, right? Well, the way we resolve is that my initial assumption must have been false. My initial assumption was that there were finitely many primes, right? If that is in fact false, then there must be infinitely many primes. All right, so let me add just a little bit in here. This implies Q is prime, which is our contradiction. Okay, and there's our proof. Right, this is how proofs by contradiction work. Right, hopefully you kind of see the layout now. Step number one, you assume the opposite of what you're trying to show. Then you start making arguments, right, until you come to a contradiction. And my contradiction is here. The Q is both composite and prime. That's not possible, so let me label these, right? These are the contradiction. Therefore, my initial assumption must have been false, because that's the only way to resolve the contradiction, right? My initial assumption was false, so there must in fact be infinitely many primes. So that's a nice little proof. It's kind of a classic example of how we do a proof by contradiction. So in the next lecture, we're going to kind of follow the same sequence that we did when we talked about divisibility of greatest common divisors. In the next lecture, we're going to look at a couple of theorems related to prime numbers. And then in the following lecture, we'll take those ideas and use them to show the fundamental theorem of arithmetic.